Hi, and in this program I'm going to be looking at coils of wire, and they might seem very unimportant, but actually they get used in all kinds of things. They're used for making electromagnets, which are used in electric motors like this one here, and they're used in transformers like these here where there's two coils of wire, and even big transformers like this one here, which is a power supply for use in a valve radio. So coils of wire, and loudspeakers for transistor radios and things. Coils of wire are very important. Here are some coils I'm going to be using. Don't try and buy them off the internet, but you could buy the wire to make this. It's 0.38 millimeter diameter wire, enameled copper wire. Make sure it's enameled copper wire and not just copper wire. Enameled copper wire has a plastic coat on it, so it insulates it, although it looks like bare wire. And this also is enameled copper wire, and this is 0.75 millimeter diameter enameled copper wire. And this is an old telephone relay electromagnet, which is essentially just a very big coil of very fine wire. I don't suggest you go looking for one of these, and I certainly wouldn't pay more than £5 for it if I was going to go and buy one of these. Here's some strong magnets that I'm going to be using today. I'll also be using today a small loudspeaker. Typically you find these in little radios and things, and a transformer and an electric motor which just happens to have a gear on it. I don't suggest that you go out and buy these things. You'll probably find some little loudspeakers in some old radio that someone gives you to take apart at some point. The transformer, you find old transformers in old junk again if you want to try and do some of these experiments with them and you want to mess about with one. And then the motors, again, that came out of old stuff. You can buy motors new if you like, but this was perfectly adequate for what I wanted to show. One of the amazing things about electricity is that when you have a piece of wire with an electric current flowing through it, there will be a magnetic field around that piece of wire. So I'm using my trusty 6-volt battery pack here, and let's see if we can use this normal navigation compass. And if I just connect those up, and you can see the compass needle deflecting, and if I just connect it the other way on the battery, so I've swapped the negative and positive over, and you'll see the compass needle deflects the other way. So there's a magnetic field caused by this electric current. So I've got a coil of wire here. The current supplying the bulb flows through that coil of wire, and let's see what happens when I connect that. Wow, the deflection there on the compass is quite substantial. And if I connect it the other way, then you'll see it deflects the other way. So what makes the magnetic field around a coil of wire so much stronger than the magnetic field around a single wire? Well, perhaps it's easier to explain with this coil here. If we imagine that we've got one strand of wire like this, and that's maybe got 1 amp of current going through it, and so it has a magnetic field of whatever strength, 1 unit of magnetic field strength. And then we take another strand of wire that's also got the 1 amp going through it, because remember these are in a coil, so that 1 amp is going through all of them. Then we've suddenly got the magnetic field from one strand of wire plus the magnetic field from the second strand of wire. So it's twice as powerful, twice as strong magnetic field. If we add another strand of wire and another, we rapidly end up with a multiple of strength of the magnetic field from the original magnetic field of a single wire. So 10 turns, 10 times the strength. 100 turns, 100 times the strength. And that's why we use coils like this, coils of wire, to generate stronger magnetic fields. So we've seen how essentially a coil of wire can create a magnetic field, but there's also a phenomenon that goes the other way. And in order to investigate that, I'm going to have to use this very sensitive measuring device, an oscilloscope. Well, here is my oscilloscope, And you can think of an oscilloscope rather like a chart recorder. The paper is now moving this way, and I've set it up so that it's 1/5 of a second or 200 milliseconds per division here. So, and it will basically measure voltage with time. So you can imagine there's a needle just here, and if I put this 1.5 volt battery across it, it's going to deflect that needle. As it happens, I've set this up for 2 volts per division. Let's just switch that to 1 volt per division. There we go. And then we can have a look and see what happens when we connect the battery across the probes of the oscilloscope. So that's coming into the oscilloscope just here. Just connect that battery. And look at that, suddenly the needle of my chart recorder flicks up by 1.5 divisions, or just a little bit more, because this battery is just a little bit more than 1.5 volts. And there you have it. What happens if I take 2 batteries, one after the other? Well, as you know, that makes 3 volts. Let's connect a 3-volt battery onto here. Here it is, here's my battery holder. I'll just connect that up, and you'll see that it will deflect then approximately 3 divisions upwards. Of course, if I connect it the other way around, then it will deflect 3 divisions downwards. As you can see, I'm sort of scraping the wires, so these connections are a bit dodgy. But there you go. So that's what an oscilloscope does. And I can change the speed of the trace. So I can make it run faster or slower, the paper, sorry. I can make it run faster or slower effectively, or I should say the imaginary paper. And I can also change the sensitivity of the oscilloscope. I'm not suggesting you out and buy one of these yet. This is probably £250 worth, so you'll have to stick to your trusty multimeter for now. Well, here's my telephone relay electromagnet, and I've connected it to the oscilloscope via these cables. And now what I want to show you is another phenomenon, which is the fact that not only can we use a coil of wire in order to create a magnetic field by running electricity through it, we can also get electricity by changing the magnetic field in which a coil of wire is sitting. So here's my coil of wire sitting here, and I've got my 2 strong magnets, one after the other, connected together here. They're stuck together, I can hardly pull them apart. And what happens on the oscilloscope if I move these magnets around? Look at that, a massive trace. You can see that as I pull the magnets away, we get a spike going up, and as I put the magnets towards the electromagnet, we get a spike going down. So there we go. We're actually generating some electricity in that coil by varying the magnetic field. Now, there's some people who say that the pyramids were an ancient way of creating energy from the Earth's magnetic field. The thing that you need to know is that you can only create energy or electricity from a magnetic field when it changes. You can't create energy from a constant magnetic field. If I leave that magnet stuck on there, well, you see that the trace shows 0. Whereas as soon as I move the magnet, in other words, change the magnetic field, I suddenly get all these pulses and things flicking around there. And if you look at the oscilloscope, you'll see that it's 200 millivolts per division. So in other words, that's 1/5 of a volt. So we're generating as much as a volt here. In terms of the voltage that we're creating, the electrical pressure that we're creating here. Now here's the telephone relay, the big coil I had earlier, which I used as an electromagnet, and I've shown you how by running a current through it, it can become magnetic, and I've shown you how by changing the magnetic field around it, we can generate a current. So, well, what if we put 2 coils together? What I've done here is I've connected the oscilloscope probes onto the telephone relay electromagnet, and we're going to, instead of using, we could of course just take the magnet and use the magnets to change the magnetic field around it, as we've done before. But let's actually take another coil here and put it really close, and then I'm going to use my 6-volt battery pack to use to create a magnetic field around this coil. So as this magnetic field changes as I switch it on and off, we should see what happens with the other coil. So, and there you see it, some little spikes. So each time the magnetic field appears as I connect this coil to the batteries, it makes a spike one way, and then when the magnetic field disappears as I disconnect the coil from the batteries, it makes a spike the other way. And if I just make the trace on this run a little bit faster, so we might be able to actually see the spikes a bit better. Yes, there they are. And there are quite a few volts there. So what have we done here? We've basically we've created a magnetic field using this as an electromagnet, and then we've converted that magnetic field back into electricity here. And devices to do this are already out there on the market called transformers, and they're a very useful way of turning one voltage into another voltage. Transformers come in all shapes and sizes, from these rather hefty beasts for working with the mains electricity, and in this case this turns the 250 volts mains into about 350 volts for use in valve radios and things. This toroidal transformer is used for 12 volt from the mains electricity. This is a transformer that's come out of the power supply in a laser printer, and this is probably not a mains transformer, but will use the alternating current that's generated actually within the printer itself, and I'll talk more about alternating current in a little while. Then there's very small transformers. Again, that one I think was from a laser printer, this one from a laser printer, and this one is a radio frequency transformer for use in some kind of radio tuning circuit, or intermediate stage between amplifiers in a radio. So it's a transformer is what it boils down to. So here we go. And of course, you'll often see transformers outdoors where they're actually transforming down from 11 kilovolts, 11,000 volts, down to 240 volts for domestic use. And here is a toroidal transformer. So it's got a coil. Well, it's got a number of coils around it. It's got one coil which normally would be connected onto the mains electricity, and we've actually connected that to the oscilloscope probes, so that's what we're going to be seeing the trace for. And then it has two other coils which would normally, if this was connected to the mains electricity, would give us 12 volts each. And we're going to ignore the black and the grey coil, put that somewhere out of the way, and we're going to just see what happens when we connect onto the yellow and red leads here, which connect to one of the coils, connect those to the 6-volt battery, and watch the trace on the oscilloscope. And as you can see, there's quite a big voltage there. Now, of course, because we're not doing this with a nice waveform as you'd normally expect from mains electricity, what we're getting is a rather horrible trace here as I connect and disconnect these batteries. But I can assure you that if we were to connect this properly to the main supply, we wouldn't be looking at something as horrible as this. Well, I've done the decent thing, and I've taken this toroidal transformer and I've actually connected it to the mains electricity. I'm not going to touch that. I don't suggest you just randomly connect transformers to the mains, or you're liable to get some very nasty explosions and possibly take out your fuse box. So this is intended for mains connection, and it's got two secondaries, and I'm looking at the voltage coming here, which is about 40 volts peak to peak on the across this particular coil, which has got the red and the yellow connections. And you can see the waveform here is what's called a sinusoid, or a sinusoidal waveform, and it's also going positive and negative. So if that's the central line, so it goes positive for a bit, then it goes negative for a bit, then positive for a bit, and it just happens that this is 50 cycles per second, so it basically does a complete wave every 50th of a second. Now, this particular shape of waveform is absolutely perfect for transformers, because what happens is that when you put this waveform into a transformer, you get exactly the same waveform out of the transformer. And it's something to do with the fact that as the voltage is changing and the current is going backwards and forwards, so you've got this continuously changing current, which means you've got a continuously changing magnetic field. And of course, a continuously changing magnetic field induces a voltage across the secondary windings of the transformer. So this is a very efficient way to transfer power around, which is one of the reasons why we use alternating current in our mains electricity rather than direct current like you get out of a battery. And now, without further ado, I'm going to unplug this before someone gets an electric shock. As you've seen, if you put electricity through a coil of wire, you get a magnetic field. And if you set up that magnetic field so that it can oppose a permanent magnetic field, perhaps created by some magnets like these, then you've got some motive force. And if you set up your electromagnets and your permanent magnets in a special configuration, then lo and behold, you have an electric motor. And so there's the electric motor. It's got a gear connected to it, and there we go. But we can also use a motor with permanent magnets like this as a simple generator, and that's what I've done here. I've got a resistor and an LED connected on here, and simply by turning the wheel on there, I can basically make the LED light. Here's another example of using a coil next to a permanent magnet, the loudspeaker that we'd use in a cheap transistor radio. And if I just connect across its two connections a 1.5 volt battery, you might be able to see that the membrane, or the black paper there, actually moves and also makes a noise. The loudspeaker consists of a coil next to a magnet, and it can work in generating sound from an electrical signal. If, of course, we make a sound and that black membrane there vibrates in sympathy with the sound, it's going to move the coil next to the magnet. Are we actually going to be able to generate any current at all from that and use it as a microphone? Let's take a look at our oscilloscope and see whether we can measure anything. So if we look on the oscilloscope and we just tap the membrane on the front of the loudspeaker, you can see that it's certainly generating a little bit of electricity. We've got the oscilloscope on very, very sensitive at the moment. It's a tenth of a volt per division. And if I just pick that up and I hold it next to my mouth as I'm speaking, we can see that it is in fact picking up my speech. So that's the effect of the coil moving next to the magnet and generating an electric current. And actually, as a child, I took two loudspeakers somewhat similar to these, made a very long piece of wire between them and used it as an intercom from one room to the next. Of course, it was extremely quiet. You could only just hear it because there was no amplifiers involved. But essentially, the current generated by one loudspeaker from the vibrations of a voice could cause the other loudspeaker to vibrate in sympathy. I hope I've given you some idea of the power of coils of wire and how important they are in electricity and electronics.